Hi everyone, my name is Rocco.
I'm Anthony.
I'm Gary.
And I'm Napoleon.
And we are senior mechanical engineering students graduating in the spring of 2023, and this is our senior design project. Our project was creating a prototype CubeSat for a technology demonstration and a proof of concept. So CubeSats are small satellites belonging to a class called nanosatellites, which are determined by their standardized form factor and low weight, which you can see an example on the right image from a CubeSat manufacturer and on the left from a NASA CubeSat. So because of their small size and relatively low cost, CubeSats are ideal academic projects.
Our problem statement was to design a CubeSat that will test an additively manufactured frame material, collect on-orbit frame temperature data, and transmit that data to a ground station. We determined that the CubeSat should be high quality, durable, meet the requirements for launch laid out in the Cal Poly and NASA handbooks, and must not exceed $2,000 for the final launch hardware. The project should be completed by the end of the spring semester, May 2023. Additionally, Quinnipiac University has never built a CubeSat, so this was our first foray into space engineering.
So regarding the frame design, the proprietary Ultim 985 resin thermoplastic frame houses the main systems on their respective printed circuit boards. So the focus of the design was 3D printing components to replace off-the-shelf parts, making them less expensive and more lightweight. For example, the frame design, antenna system, and solar panels will be made from the thermoplastic and will allow us to keep the budget of the CubeSat hardware under $2,000, as you can see from the prototype and the exploded view on the slide.
The antennas are secured to the rotating disc within the CubeSat frame until deployment, which is achieved through a preloaded torsion spring, held in the preloaded position by a nylon wire running through the disc. When we are ready to deploy, there will be a signal to a transistor seen on the circuit is seen on the left, which will then send current to a burning resistor, which will then burn the tense nylon wire, releasing the tension that holds the disc in place, and the spring will rotate to force the antennas through the slot to the exterior of the frame, which the deployed antennas appear as they do on the right side.
So, and now for the internal system workflow, which we'll break down over the next several slides.
Okay, so our electric power system consists of solar panels, rechargeable batteries, and power controllers. Solar panels, you can see on the left there, are assembled on every side of the CubeSat to power all the systems and charge the lithium-ion batteries, which are on the top, the green, when sunlight is present in orbit. When sunlight is not present, the power regulating charge controllers will switch system power solely to the batteries. You can see the charge controllers in the center. And this cycle will repeat each orbit to keep the satellite powered during all stages of the mission.
So our data handling system uses a Raspberry Pi Pico to control the subsystems. For the temperature measurements, 16 thermistors are used inside of the pillars of the frame, which send analog data to the ADCs and then to the Pico. These are then stored on an SD card and prepared to transmit.
Our communication system uses a radio that operates at 433 megahertz and a cross-dipole antenna. It is important to note that this frequency lies within the U.S. amateur radio band, which required me to obtain an amateur radio license to use. To briefly explain the diagram up to the right, the radio will receive additional signal from the Raspberry Pi and convert it to analog signal. This is then fed through a quadrature circuit, which splits the signal into 4 parts with a 90-degree phase shift between each signal. This is done to achieve circular polarization, which increases the gain and range of the radio. Many of the engineering characteristics chosen for this project were selected based on standards outlined by the California Polytechnic Institute and testing requirements established by the Aerospace Corporation and NASA, and specifications needed to carry out this CubeSat's mission. Below is a table of our engineering characteristics.
So over the course of the academic year, we were successfully able to create a frame, antenna deployment system, and solar panel assemblies which adhere to our problem statement. So on the slide, you can see our team there. From left to right, you see me, Rocco, Gary, and Napoleon.
So to conclude, our team has laid the foundation for future CubeSat project teams and created the main 3D printed assemblies. So this project would be termed CubeSat 0, as it is a proof of concept that our idea can work, but it needs to be finalized in what would be CubeSat 1. So future teams can continue this project by working on the circuitry and data systems, and we hope that Quinnipiac will eventually have a flight-ready CubeSat.